video, I have some comments to make on the effects, how the substrate leakage in CMUTs can affect spring softening effect, and how it reduces the receive performance of CMUTs at low frequencies. So if you have seen the previous videos, I'll just highlight this quickly that in literature, you can see some of the papers, previous literature or published work on CMUTs. So this is from 2004 IUS conference, and what these people observed in the real part of the impedance was that the substrate tends to have more leakage at low frequencies as compared to high frequency. So what they were doing was to build CMUTs for high resolution imaging for intravascular probes. So in order to reduce this effect, the baseline that you see, which is elevated and has sort of a negative slope with frequency, so you can see the real part is decreasing with frequency. To alleviate this problem, they thinned down the substrate to about 200 microns. So again, it was a very thin substrate, but the picture is not here. I'll just put the reference in the description. You will see that when they thinned down the substrate, there was increased ringing at low frequencies, which again comes at the cost of very high leakage at low frequencies or at DC as compared to high frequencies. So this problem is not only reported in this work, but again, there are some airborne CMUT transmitters which were built in Pilkington University in 2018, and we have a very similar trend of you can see that the real part is decreasing with frequency, and has a negative slope which is elevated as well. So this trend not only sort of it's not only that the real part is decreasing with frequency, it's also affecting the quality factor of resonance. I mean, the bandwidth is more. For example, this was characterized. If you've seen the previous video on my channel, you will see that in the circuit models we have a mechanical loss, which accounts for the damping loss of electric waves in the backing medium. So if you remove that loss, you will have a very high Q resonance. Okay, so this loss is also affecting the quality factor. So you can say that CMUTs which are built with which are produced with very thin backings, but I'm saying thin again. Thin means that the physical length of that substrate is small compared to the ultrasonic wavelength or the operating wavelength of CMUT. Okay, CMUT might have a very large wavelength at the front medium because for fluids or for air for which applications they are produced, the longitudinal speed of sound in air is much smaller than that of in solids. So at the same frequency, you're going to have a very large wavelength in the backing solid. Okay, so if that thickness is small, if the substrate is not considered as rigid or solid, then you have this kind of a trend. And all these three, in all these three cases, different cases, which are produced at different times and reported in literature, you see these baselines. Even in the last reference you see over here. Now, what these people claim that is that they, through Doppler vibrometer measurements, they have observed lower order Lamb wave modes in the substrates. So you can see that the baseline is not, it's still not flat. Okay, there are some reflections from the structure or the posts of the substrate in the range of about 1.6 megahertz to 1.8 megahertz, and then they have a operating frequency at 2.1 megahertz. That's the fundamental resonance of the vibrating plate, and this vibrating plate tends to couple some of the energy into the backing as well. Okay, in form of tensile stresses, and these stresses are sort of you can see that the effect that it creates, it reduces with frequency. Okay, so the effect is dissipative, so it has to be modeled with the loss on the mechanical side of CMUTs, as can be seen over here. And this loss also affects the quality of your resonance. Okay, if I remove this, I'll show you later on that you will have a very high Q resonance in as you have in air, let's say. Okay, So yeah, so even if you have lower order lamp wave mode, symmetrical or anti-symmetrical A naught and S naught at the operating frequency of CMUTs, you still don't have flat baseline. But one comment is that solely if it's only the lamp wave modes in the solids, then they do not create a very large negative sloped baselines like over here. Okay, that means you have shear or longitudinal elastic waves instead of just lamp wave modes, which create the tensile stresses as such. Yeah, but you can see that the CMUTs, which has vibrating membranes, because you can see the frequencies being swept by applying a certain peak amplitude signal from impedance analyzer. And once you do that, the membrane starts vibrating, and given the structural, geometrical, and material properties, you observe a resonance. Okay, that is particular to that geometry. But in all these three cases, uh, you also observe that this elevated baseline is due to the substrate leakage. Okay, all right. Enough said about this. Let's move on. We have okay, it's not moving. Yeah, okay. So we have two models, two competing models. The first one that you see in above is it includes the RC shunt branch, which takes care of which accounts, or you can say which models the backing loss due to the elastic waves which are propagating down in the substrate. That has to be modeled by this RC branch. Okay, this is a mechanical loss. It appears on the mechanical side. So uh, in the in the in the other model, you can say that the other model is, let's say, is having a thick or a rigid substrate. So the shunt branch across the transduction force in the model, it's a very high impedance, so it's modeled by an open circuit. Okay, so the only difference between these two circuits are receivers. Okay, so you can see that the acoustic termination, acoustic port is terminated not only in the radiation impedance, but it has a dynamic force, um, which is experiencing due to the incoming ultrasound pressure of force. Okay, and because of that force, you're going to have an certain open circuit voltage, a time varying open circuit voltage on the electrical side of the model. Yeah. So the only difference in these two circuits, in these two receiver circuits, is that you don't have over here. It's for this. You have the open circuit conditions for rigid backing. In part A, you have this RC shunt branch across the transduction force, which models the damping of elastic waves in the solid medium. Okay, and it's a mechanical loss, not electrical loss like acidic capacitance or you can also have in the electrical side the conductance due to the passive films like aluminum or silicon oxide, right? Yeah, so it's a linear model, and you don't see the force which is in a full blown large signal model. It's proportional to the applied voltage. Okay, so it's the other way around. For receivers, you have a linear small signal models, and the force is linearized. So this electromechanical turns ratio and the spring softening capacitance is handling that force. Okay, so over here you have, if you calculate from this node down to this node, I mean the voltage or across this shunt branch is the transduction force. Okay, that's what the transduction force is for the linear receivers. Okay, yeah. So the difference between these two models is explained over here. If you have a thick or a rigid substrate, okay, you don't. It's very large impedance, so you have open circuit conditions across the transduction force. So you can see a very high Q. And the frequencies in both cases are the same, but you can see the effect is that you have a very high Q resonance, which is not the case that if you have a case of a thin backing. It is a finite, the substrate thickness is finite, but it is much less than or smaller than the wavelength of the CMUT, the operating wavelength of the CMUT. So you can see that the Q is lower, is much lower in the left side on the in the case when you have a thin backing, right? Yeah. So what you have to do is, I mean, you can see the measured resistance and the measured reactance and how well they can be characterized. That if you include RC shunt branch across the transduction force, that's not the case over here. I mean, if putting this down in this figure, it's not going to characterize your measurement, right? For vapor bonded CMUTs having thin substrates. So you have to include the mechanical loss. So I'm just trying to comment on that why this RC shunt branch is important to model those elevated baselines, which has a sort of a negative slope that models the leakage to the substrate. Okay, so RC it has both real and imaginary part, and the reactive part of the, the reactive part of the substrate leakage is can be thought of as a compliance of the backing plate. So you can think of it as a bilateral CMUT. For very thin substrates, we know that uh, the the peak displacements are not zero, as in the case of rigid substrates, right? So there is certain displacement. So C sub can be again compliance of the backing, which is much less than the front plate compliance, because the front plate is easily depressed. It's silicon in most cases, which is easily depressed by the ambient medium loading and the electric field that exists between the CMUT electrodes. So CRM is much more compliant, or you can say, yeah, CRM is going to have a larger value than C sub, right? Yeah. So you can see over here, the blue part is the reactive part of substrate impedance. So this impedance is impedance of this branch, RC branch, which is modeling your which is modeling the damping, sort of a damping of elastic waves in the glass medium. So well, and this when these curves they go into the model over here, then they start creating these kind of baselines which are being measured. Okay, and where they come from? Well, one way to look at this problem is to just go ahead and fit this in the model and say that, okay, yeah, you see that how well this measurement can be explained by the fitting, but where does it come from? It comes from finite element analysis, package calculations of if you have a 2D symmetric model with the thin backing, you can assuming that that thin backing is isotropic or homogeneous medium of let's say glass or whatever silicon it is, and you have to introduce isotropic loss factors. Okay, it can be anisotropic, but that would be difficult. You need to have some knowledge of the matrix, which is difficult to predict. So if you start introducing isotropic loss factors into the um, into that axisymmetric backing, then you start looking at those baselines in the impedance of CMUT cells, right? Yeah, so that loss factor is what is responsible to creating those baselines, because those loss factors means that you have a certain damping of dispersive waves in the backing medium, which are being propagated by the vibrating membrane. Okay, so that's the idea. They're coming from FEMs, and you have to include that loss in if you're modeling that by a circuit model. So you have to include that loss by or right across the transduction force, and then you can reproduce that. Okay. Yes, I think I have yeah. So if you should look at into if you're interested to see how it can be done on console, I've already uploaded a video before. You can go and have a look on that. So you will have an idea how these baselines are created in console. Okay, right. So but what I wanted to comment on the what kind of effect that the substrate loss has on CMUTs is that let's say you have a certain bias that you have applied between the electrodes, and as you can see, for these geometrical parameters, for the same geometrical parameters, the measurement was as such that you have about 77 kilohertz. The measured resonance is at 77 kilohertz, right? So if it is 50-volt biased, it's the same frequency, almost the same frequency. So if you remove the leakage, if you do not have that RC branch across the transduction force in the model, Well, the difference with leakage and without leakage in the sensitivity, in the magnitude of the sensitivity, is about 1 millivolts per pascals. What happens if that bias is double? Okay. Well, as expected, due to the spring softening effect, the resonance shifts down. Okay, so it's not 77 kilohertz, it's now 75 kilohertz over here. And as you know that uh, if the membrane, if you're going to increase the bias, your membrane is going to come closer to the substrate. That means you have a higher coupling conditions. That's one. The other is that the electric field sustained in the cavity is large. So the beside higher electromechanical conversion ratios, you're going to have more change in capacitance. So as a receiver, CMUT is going to have more because there is a very thin gap that is going to remain between the silicon and the glass. So you're going to have, for incoming ultrasound or mechanical disturbance, you're going to have a very large current at the output or voltage for that purpose, you see. Yeah, so the sensitivity is going to improve. That is because the electric field strength is increasing, and that increases the transduction in the cavity. So you can see that from 7 millivolt Pascal, this is 10 to the power minus 3, you can see over here. So from 7 millivolts per Pascal, it increases to about double. That's about 15 millivolts per Pascal. But what happens with the red curve? That is, if you have that RC branch, well, it doesn't let, first of all, it doesn't let the frequency to shift down. Okay, it kills the spring softening. The other thing what it does is that the difference between with including that RC shunt branch and without an RC shunt branch. Uh, so including the mechanical loss and without including the mechanical loss, the simulated results show that the difference due to the leakage grows. So in this case, the difference was about 1 millivolts per Pascal. Over here, you can see the difference is like, it's like 15 millivolts without leakage, and over here it's about less than 4 millivolts. So the difference is about 10 millivolts per Pascals, 10 millivolts per Pascals. So you are started losing. I mean, this red curve is going down with the bias, right? Because of the substrate loss, and the quality is again lower, right? But you can see first of all, there is no shift in frequency, and the other thing is that uh, due to the leakage, you are losing more to the substrate. So it kills the spring softening as well as it compromises the sensitivity of CMUT cells if you have leakage. Okay. And what happens if I increase the bias to about 4 times? Well, the simulations will show that, as expected, without leakage, the frequency is going to shift down because of the spring softening capacitance, CRS, in the model. It is this capacitance which is shifting the frequency. But if you have C sub, it's going to kill that spring softening and it's not going to let the frequency shift down anymore. And that is going to stay over there. Okay, you can see in all these three curves, there's no spring softening effect. There is no shift in the frequency with bias. Go on increasing the bias, it stays there. Okay. Yeah, but before collapsing the cell, as you go on increasing the bias, since the silicon plate is moving very close to the substrates, the frequency is shifting down, but you can see that the leakage is also increasing. If you don't have any leakage, then that is like 40 millivolts per Pascals, and the difference rises. This is like 1 or 2 millivolts per Pascals, and you can see the difference over here and then over there. The difference is rising. You're losing to the substrate, but you're losing to the substrate at the same frequency. That's interesting. So substrate loss, number one, it kills the spring softening. Okay, this C sub is like a notorious capacitance, and it's not going to let CRS take its effect from the bias. Okay, so it's going to kill the spring softening. The other thing is that this loss is going to affect the sensitivity of the CMUT cells, even if you have a very large coupling coefficient at when the membrane is biased very close to the substrate, you're going to compromise the sensitivity. The sensitivity is compromising even with at a very large coupling coefficients. Okay, yeah. So no need to bias the membrane very close to the substrates. You're already losing the CMUT uh, receive sensitivity. at large biasing, at large biasings. Okay. Yeah, so these three curves on the upper rows are the magnitudes for different biases: 50 volts, 100 volts, and 200. And the lower ones are for the phase. Okay, and you can see for the blue curves, there's not much of a difference. But with spring softening, the frequency is changing, and that's how where the phase changes, right? But you can see the phase at 77 kilohertz is there with leakage. You don't have any spring softening neither in phase nor in magnitude. Okay, so yeah, it stays over there. So that's an interesting finding I wanted to share. But this is not just a claim that I'm making in this video based on equivalent circuit models of CMUTs. Let me show you some of the measurements. And you can see in these measurements, well, let me talk about this curve first. I'll come to this one later on. First of all, it has a different frequency. It's not 77 kilohertz that I'm showing over here all the time, like this or this one. Okay, and what is measured before. It's a different frequency, so it's a different story. It's a different cell. Actually, these cells were supposed to be collapsed. Yeah, but we couldn't seal them quite effectively, so we had some air left. So we had to, if you look at the left figure, we had to collapse them by applying more bias, I remember. So you can see that after 50 volts, after certain application of bias, more than 50 volts, around 60 volt, it collapses. And then there's a trend that the frequency shift to the right, and that's collapse. You can also see that the baseline in the collapse baseline are different than the uncollapsed baseline. So one thing to notice in all these measurements is that these are conductance curves. Okay, if you plot them, the data is conductance. So if you plot them the other way around in ohms, uh, 1/G is ohms, right? So yeah, that means the collapse is losing less energy to the substrate. It's the other way around. So collapse does not leaks much energy as compared to uncollapse. The baselines are different. That's the first thing. The second thing is, you can see in this cell, like I was saying, um, as you go on increasing the bias, well, it doesn't move. The frequency stays there. Okay, these are different geometrical parameters, but at a particular frequency, it stays there. And this trend is not about this particular CMUT. Let me share some other cells as well. For same geometrical parameters, these are different cells. And you can see for different biasings, as you go on increasing the biasings, the frequency stays there. So the spring softening effect is just gone if you have those mysterious sort of conductance baselines which are increasing with frequency, or if they are decreasing with frequency if you plot them on a resistance scale. The spring softening is gone. So that's what the model predicts, and that's what the measurements are telling over here. But and if you're more interested to see what happens after collapsing, then once it is collapsed, you have a less leakage. But yeah, the frequency does shift because the compliance capacitance is its takeover. So this frequency shift is due to this compliance capacitance. It becomes a non-linear. So because once the CMUT collapses, you know that uh, you don't have a linear or a well-behaving spring which obeys Hooke's law, right? Some of the part is collapsed and some of the part is still hanging from the parts where it is bonded. Yeah, so that sort of that creates negative, or not negative, but a nonlinear compliance, which is a function of the membrane profile, right? So the spring is hardened; it doesn't obey Hooke's law. But if this CRM becomes small, certain part of the membrane is collapsed. It's not a linear spring. So you can imagine that 1 over LC is going to be large. It's going to shift the frequency towards right, and then it goes on. As you increase bias, the spring is hardening. There is a hardening effect. Compliance is decreasing. The contact radius is increasing, and you can see with the voltages, it's increasing. Okay, and the other figures are they don't give much of information, but if you're interested, I can just talk about this. That if you do this in the reverse from 100 volt back down to, let's say you go to this green one is 60 volts, that's where it's still collapsed. Okay, the contact radius is decreasing in this figure. Yeah, but at around between 50 and 60 volts, uh, where the snapback occurs, right? So in that region, uh, that's a different state of CMUT, but once 50 volt is applied, the membrane is lifted off of the substrate, so it becomes uncollapsed. Okay, and then it stays there. Even in the reverse direction, the frequency is not moving. What happens in this region? Well, there is some finer step sizes, 50, 52 volts, 54 volts. There's a not difference of 10 volts, yeah, 2 volts. So it decreases, and then this is a snapback region, which you can see the conductance is decreasing and then starts shifting. So at 60 volt, it does collapses. Okay, but this you can see it does collapses before 60 volts, before because the frequency they start shifting towards right. Spring softening effect. There is no spring softening. There is a frequency shift because of collapse over here. And this is also collapsed. This is in the reverse direction as before. This is even finer voltages. You can see that has been applied for the impedance analyzer. And yeah, these are snapback regions. Very interesting, but hard to explain what is going on in here. Uh, all I can understand is that yeah, it's not the spring softening is just here up until 55.3, and then the violet one is where you have a shift of frequency. So maybe 50.4 is a correct measured collapse voltage of the particular cell, and then it sort of the conductance is reducing, but the frequency is shifting towards right. Yeah. So well, some comments on breaking loss, and in particular, if I talk of the uncollapsed states of CMUTs, there is no spring softening if you see these baselines. Okay, so this is what I measure, and based on the data, and this is what we have simulated. Okay, so the spring softening is gone, and as well as the receive performance is compromised. Okay, so that's all. Thank you for listening, and have a very good day.